Hello everyone, my name is Honesto Pardede. I am mechanical engineering student from Udayana University. Here I want to represent about metallurgy on modern alloy production. Here I got the references from the Metallurgy for the Non-Metallurgists, second edition by Arthur C. Riordan. We got to the content, we got 5.1, the effect of alloy on solidification, 5.2 solidification structure, 5.3 melting furnaces, 5.4 molten metal processing, 5.5 primary production casting, 5.6 foundry casting, 5.7 non-ferrous casting alloys, 5.8 powder metallurgy. We jump to the 5.1, the effect of alloy on solidification. The solidification of alloy is a complex process and is most easily understood by explaining how the solidification characteristics of alloys differ from those of pure metals. This is a topic discussed to some extent in chapter 2 and is briefly expanded in this section. We got solidification of pure metals. Where a pure metal begins to melt, the solid liquid mixture stays at the melting point temperature until all of the solid has completely melted. The amount of thermal energy needed to complete the transformation from solid to liquid is defined by the latent heat of fusion of a material. For example, pure aluminum begins to melt at a temperature of 660 Celsius and has a latent heat of fusion of 398 kilojoule per kilogram. If 1 kilogram of solid aluminum is heated to 660 Celsius, then the addition of 398 kilojoule of thermal energy would be required to completely melt the aluminum. Although heat may be continuously applied, only after the material is entirely liquid, thus the temperature begins to rise again. Conversely, pure metal give up their latent heat of fusion and solidify at a single temperature. If a pure metal is melted and allowed to solidify in a melting crucible, a thermocouple placed in the metal during solidification could trace a cooling curve like that shown in figure 5.1. In my slide, we can see the characteristic cooling curve. We got three figure here. The A for pure metal with no foreign matter present, and B for pure metals with foreign matter present. The presence of impurities reduce the amount of supercooling because impurities produce a strong nucleating effect, but the melting point itself remains unaffected. For the C is a typical cooling curve for a solid solution alloy. Note that freezing occurs over a range of temperature. And we got solidification of alloy. The solidification of alloy is more complex than that of pure metals because the different elements in an alloy possess different melting temperature. Pure metal freeze and melt at a specific temperature. Alloy freeze and melt over a temperature range. The result is a so-called mushy zone for an alloy solidification under equilibrium condition. The mushy zone represents the temperature extremes between which a two-phase solid or liquid composition is present. The temperature at which solidification begins is called the liquidus temperature, and the equilibrium temperature where solidification is complete is called the solidus temperature. Different alloy composition have different liquid and solidus temperatures, and the lines that appear on a binary phase diagram that differentiate this region from each other and revert to as liquidus lines and solidus lines, respectively. When some of the liquid metals begin to solidify at the liquidus, the technical term for this event is freezing. Freezing continues until solidification is complete at the solidus. And we got the figure 5.2, the aluminum silicon phase diagram with S-cast microstructure of alloy with various composition above, below, or near the eutectic composition of 12.6% Si. Alloy with less than 12.6 Si are referred to as hypoeutectic, those with close to 12.6% eutectic, and those with over 12.6% SIS hypereutectic. And for figure 5.3, we got a loss foam casting of an automotive engine block. We got to next 5.2, solidification structure. Solidification structure. The solid-liquid interface during solidification normally exhibit one of three types of crystal growth in the liquid: planar, cellular, or dendritic growth. As shown in figure 5.4, as we can see, the effect of undercooling on solidification structure. The type of growth is controlled by the manner in which heat is removed from the system. When the liquid ahead of the solid-liquid interface has a positive temperature gradient, heat is removed from the liquid by conduction through the growing solid. Because the temperature gradient is linear and uniformly perpendicular to the interface, a smooth interface is maintained, and the growth is planar into the liquid. When there is a temperature inversion and the temperature decrease ahead of the solid-liquid interface, then either cellular or dendritic growth will occur. The difference between the two is a matter of degree. Small undercoolings tend to produce cellular growth, while large undercooling tend to produce dendritic growth. In pure metals, undercooling can result from thermal supercooling, while in alloys it can result from a combination of thermal and constitutional supercooling. And in figure 5.5, we can see transition from planar to cellular growth. It's occur when the advanced planar solid-liquid interface become unstable and a small spike appear on the interface that then grows into a cellular type structure. The planar surface become unstable because any part of the interface that grow ahead of the remainder enters a region in the liquid that is lower temperature. The initial spikes that form remain isolated at first because as they grow by solidification, they release their latent heat of fusion into the adjacent liquid, causing a localized increase in the temperature. Consequently, parallel spikes of almost equal spacing advance into the liquid. And on figure 5.6, we got a scanning electron micrograph of dendritis in the shrinkage region of a stirling casting. Original magnification is 42 times. And then we get to the figure 5.10. It's a solidification in an alloy with a wide freezing range. A and B is the early stage, and C and D is a later stage. Non-dendritic solidification for semi-solid processing. Although nearly all commercial alloys solidify dendritically with either a columnar or an equisized dendritic structure, an important exception is non-dendritic solidification for semi-solid processing. Semi-solid alloys are produced with a unique non-dendritic microstructure. With important advantage for bulking shaping, semi-solid alloys flow easily and can be injected into a mold cavity, much like the injection molding of plastics. This behavior arises from the globular microstructure of a semi-solid mass. Next, we got 5.3, melting furnaces. A wide variety of furnace technology are available for melting metals. In steelmaking, for example, pig iron is produced in a blast furnace from iron ore, limestone, and coke because it contains excessively high levels of silicon, manganese, carbon, and other elements. In figure 5.11, we can see microstructure of a thick case or a semi-solid process. magnesium alloy. In the figure A, we can see a conventional etching, and B, we got electrolytic etching and polarized like illumination. In figure 5.12, we can see schematic illustrating morphological transition under forced convection to develop semi-solid structure. The liquid iron, together with scrap and fluxing agents, is then introduced into either a basic oxygen furnace or an electric air furnace for further refining with oxygen. The objective is to reduce the silicon, manganese, and carbon to acceptably low levels in the resulting steel. The steel is then tapped or poured into refractory line ladles or transferred to an argon-oxygen decarburation vessel for further refining. During the tapping operation, alloying elements that will determine the final chemistry of the steel are often added to the ladle along with deoxidizing materials. Steel may also be treated in the ladle before being poured into molds. The types of ladle treatment used for steel include a variety of common methods, including string or hidden process for deoxidation, decarburization, and adjustment for chemical composition, as well as guessing some example. Following ladle treatment, sometimes additional remelting or refining steps are performed prior to casting. Vacuum induction melting. Vacuum induction melting under vacuum is an induction heated crucible, is a tried and tested process in the production of liquid metals. It has its origins in the middle of the 19th century, but the actual technical breakthrough occurred in the second half of the 20th century. Commercial vacuum induction melting was developed in the early 1950s, having been stimulated by the need to produce superalloys containing reactive elements within an evacuated atmosphere. Vacuum induction melting can be used to advantage in many applications, particularly in the case of the complex alloy employed in aerospace engineering. This advantage have had a decisive influence on the rapid increase of metal production by VIM. The flexibility due to small batch size, fast change of program for different types of steel and alloy, and easy operation. As we can see in figure 5.16, a cross-sectional view of a coreless type induction furnace illustration for quadrant string action, which aids in producing a homogeneous melt. Low losses of alloying elements by oxidation, achievement of very close compositional tolerances, precise temperature control, low level of environmental pollution from dust output, removal of underside trace elements with high vapor pressures, removal of dissolved gases, for example hydrogen and nitrogen. Then we get to figure 5.17, the electric bailout crucible furnace, courtesy of Morgan Crucible. Their thermal efficiency and service life considerably. Crucibles may be as small as teacups or may hold several tons of metals. They may be fixed in place within a furnace structure or may be designed to be removed from the furnace for pouring at the end of each melt. Then we got to the next slide, 5.4. we got to the molten metal processing. Molten metal processing molten metal are processed and handled in various ways depending on the alloy and melting practices that are used. Melting is a basic way to combine elements for the purpose of alloying, and the overall chemical composition of the molten alloy must be carefully controlled and processed before casting can take place. The reactivity of molten metal at high temperatures also requires special processing technique for removing or preventing the formation of inclusion impurities or dissolved gases in the melt. As noted, ladle treatments may follow furnace melting, and in a various example of ladle treatments for steel, as we can see in figure 5.14, the example of ladle treatment used to refine molten steels. We get for picture here: A. Bottom stirring, B. Power injection, C. Vacuum oxygen decarburation process, and D. Vacuum arc degassing. When a primary furnace is emptied into a tapping ladle, the steel can be transferred into other ladles, furnace, or vessels for treatment. With ladle treatment, steel with a sulfur as low as 0.002% can be produced that are essentially free of oxide or sulfide inclusion. Then we get to fluxing of a molten metal is often the first step of obtaining a clean melt. Fluxing is a term commonly used in foundries and melting departments that refers to molten metal treatments from the addition of reactive chemical compounds or inert gases. The various functions of molten metal fluxing additives, either singly or in combined, include: A. Removing inclusion impurities or dissolved gas from the melt. 2. Preventing excessive formation of solid phase inclusion. C. Preventing or removing oxide buildup on furnace walls. And last, we get injecting or distributing alloying constitutions. Those fluxes are commonly used to some extent with virtually all molten metal operation in both a foundry and in production of mill product. Fluxing can occur throughout the various stages of melting and handling of molten metals, from the melting or holding furnaces to the transverse ladles. Molten metal fluxing agents may be chemically active solid, inert gases, or a chemically active gas. This type of flux depends, of course, on the composition of the melt and refractories, the iron and steel making. For example, the furnace of fluxes in twofold: to render the high melting refractory oxide impurities fusible and separable from the molten metal, and to provide a medium with which the impurity elements or compounds would combine in preference to the metal. Next, we get 5.5. Primary production casting. Primary production casting. The primary production of metal normally involves either ingot casting or continuous casting of products such as strip, sheet, wire, or bar. Continuous casting offers certain benefit over static casting, but not all metals can be continuously cast. Products are typically cast in ingot form for subsequent hot working reduction operation. Foundries also require the use of ingots, as we can see in figure 5.19. Automatic stagger of ingot for foundry remelting courtesy of a light metal edge that can be remelted, sometimes called pit ingots, to provide specification compliant composition. Static ingot casting. Several ingot casting processes have been designed and developed for downstream manufacturing processes. The most common is static ingot casting, where molten metal is poured into a vertical open-ended mold. The mold is made of metal. Usually cast iron is tapered along its length so that solidified metal can be easily withdrawn from it. The fundamental requirements that must be satisfied by an ingot are capacity to withstand subsequent mechanical reduction operations without rupturing or cracking, with the capability to yield at a commercially acceptable finished product. Then we get to a continuous casting processes, may be defined as the continuous solidification and withdrawal of product from an open-ended shaping mold. The earliest method of continuous casting occurred in the 18th century, with patents by sellers from the manufacturing of lead pipes in 1840 and by Lane in America for continuous casting of non-ferrous metal tube in 1843. Today, continuous casting is a common production method for steels, copper alloys, and aluminum alloys. The quality of continuously cast metal can, in certain respects, be superior to that of a statically cast ingot. For example, pipe is virtually eliminated. Significant production advantage also may be realized by reducing or simplifying the subsequent reduction operation traditionally involved in converting statically cast ingot into semi-finished product. The shape and length of an ingot, for example, can have a decided impact on the nature and number of rolling operations traditionally needed in producing plate and sheet product. Continuous casting can be either vertical or horizontal. Horizontal casting is limited to metals with lower melting point such as copper, aluminum, and cast iron. In vertical continuous casting, as we can see in figure 5.20, a schematic of vertical continuous casting processes. There we can see a molten metal, water-cooled mold, solidification zone, water sprays, and solid metal. The way molten metal is poured into the caster from the top. The temperature of the metal is reduced. It passes through the water-cooled mold. Solidification starts from the middle of the mold, beginning at the outer surface of the mold and moving toward the middle of the embryonic ingot. From this point, the liquid metal assumes a wedge shape as it passes through the solidification zone and through the first part of the water spray zone. All the metal is solidified from this point forward. The solidified ingot may be handled in several ways. For instance, while the ingot is growing in length, it can be directed into a holding pit. At the appropriate time, the continuous caster can be set down in a section of it can be cropped and removed from the holding pit. Then the process can be restarted. This is known as a semi-continuous casting. In another process, the product is bent so that it emerges horizontally from the casting machine. With this setup, casting time is limited only by the amount of liquid metal that can be supplied to the caster. The product can be cut to any desired length, or it can be fed directly into other processing equipment. Specific grades of aluminum, stainless steel, and copper are commonly produced using this method. Next, we got to 5.7, non-ferrous casting alloys. In terms of tonnage, cast iron is the most common foundry alloy, constituting approximately 3/4 of the worldwide production of casting. For example, the 14th census of casting production tabulated the total worldwide production of casting in 2005 at 85,041,78 metric tons. Tonnage of the cast alloys in the year was distributed among the various alloy systems as follows. Aluminum casting alloys. Aluminum casting alloys are the most versatile of all common foundry alloys and generally have the highest castability ratings. As casting materials, aluminum alloy have this favorable characteristic. 1. Good fluidity for filling thin sections. 2. Low liquidus temperatures relative to those required for many other metals. 3. Rapid heat transfer from the molten aluminum to the mold, providing shorter casting cycles. 3. Hydrogen is the only gas with appreciable solubility in aluminum and its alloys. And hydrogen solubility in aluminum can be readily controlled by precision methods. 5. Many aluminum alloys are relatively free from hot short cracking and tearing tendencies. 6. Chemical stability. And 7. Good as cast surface finish with lustrous surfaces that suffer few or no blemishes. I make several pictures here, as we can see table 5.1, 5.2, 5.3 and 5.4. The copper casting alloys. Copper casting alloys are available as sand, continuous, centrifugal, permanent mold, and some die casting. They are generally similar to their Rhodes counterparts, and as we can see in table 5.2, but have their own unique composition or property characteristic. For example, the ability to add up to 25% Pb, which would be possible for a Rhodes alloy, provide composition in which dispersion of lead particles help prevent galling in bearing application. Copper casting alloy are used for their corrosion resistance and their high thermal and electrical conductivity. The most common brushed alloy are the general purpose cast red brass used for valves and plumbing hardware. We can see several tables here. And magnesium casting alloy. Magnesium castings of all types have found used in many commercial applications, especially where their lightness and rigidity are a major advantage, such as for chainsaw bodies, computer components, camera bodies, and certain portable tools and equipment. Magnesium alloys and casting are used extensively in aerospace components. Molten magnesium alloy have a very low viscosity, allowing the metal to flow long distances and fill narrow mold cavities. Their relatively low solidus temperature allows the use of hot chamber die casting, and their minimal reactivity, which still below 700 Celsius in Fahrenheit was 1300, allows the use of inexpensive steel crucibles and molds, because magnesium and its alloys readily react with air in the molten state. It's necessary to use a protective flux during all melting operation. Fluxes include mixture of various proportion. Because the fluxes have nearly the same density as a molten magnesium, they generally float on the surface and form a scaly crust that protect the underlying molten magnesium. Okay, we got to next 5.H, powder metallurgy. One of the more recent metallurgy development in the manufacture of modern alloy is the development of powder metallurgy, or PM processing. Metal powders can be produced using a wide variety of mechanical methods as well as by chemical and electrochemical methods. Atomization is the dominant method for producing metal and pre-alloyed powders from aluminum, brass, iron, low alloy steels, stainless steels, tool steels, superalloys, titanium alloys, and many other important industrial alloys. Current atomization technology is the result of steadily advance over the last 70 years since the first large-scale production of atomized iron powder during World War II. By the early 1980s, atomized powder had accounted for more than 60% by weight of all metal powders produced in North America. Currently, it is estimated the worldwide atomization capacity of metal powders exceeds 10 metric tons per year. Atomization has become the dominant mode of powder production because high production rates favor economy of scale, and because pre-alloyed powders can only be produced by atomization techniques. Water atomization. In the terms of tonnage, water atomization is now the preeminent mode of atomization for metal, especially various metals powder. As we can see in figure 5.28, atomization processes used in the industrial production of metal powder. First, water or oil atomization. B, the gas atomization. C, centrifugal atomization. D, vacuum or soluble gas atomization. And E, the ultrasonic capillary wave atomization. Gas atomization is processes generally produce powder particles that differ from those produced by water atomization process in terms of their geometry and surface chemistry. Gas atomized powder are typically more spherical in geometry and possess a lower surface oxygen content than their water atomization counterparts. During the gas atomization process, the liquid metal is disrupted by a high velocity gas such as air, nitrogen, argon, or helium that is directed through a specially shaped nozzle. Atomization occurs by kinetic energy transfer from the atomizing medium to the metal. In order to visualize this process, the breakup of the metal stream into fine droplets can be compared to the way that gasoline is atomized as it passes through the venturi nozzle is an automobile carburetor. As in figure 5.29, we can see water atomization system. In point A, we can see various stages of the water atomization process. And B, large-scale system, 1,000 to 100,000 tons per year. And on figure 5.30, we can see two fluid atomization with A, a free-fall design, gas or water, and B, continued nozzle design, gas only. Design characteristic, angel formed by free-falling molten metal and atomizing medium, a distance between molten metal and nozzle. The D is a diameter or confined molten metal nozzle, and P, protrusion length of metal nozzle. Okay, I think that's all that I've got. Thank you so much.